Uh, Hello, good evening, and welcome to the sixth lecture on this course, Phase Equilibria and Materials. So this week, what we covered was mainly the phase diagrams of iron-carbon system or Fe3 system, and what are the different alloys corresponding to those system. And also we have seen different non-ferrous phase diagrams as well. So this week we'll be solving a few numerical questions based on these phase diagrams that we have covered in the past week. So hopefully you can see my screen. Yeah, that's okay. So starting on with recapping few of the concepts that we covered. So first we'll just cover in brief um, the iron carbide phase diagram. So there's a reason why we call it iron carbide, because as you will see, we draw the diagram between the extents of pure iron, 100% iron, and intermetallic compound, carbide compound called cementite. Okay, so that's the composition of cementite is Fe3C. So that's the reason why the phase diagram in between, existing in between 0 to 6.78% of carbon is called as the Fe3C phase diagram. So it looks something like this. This is the temperature scale, and here is the pure iron, and here is the carbide that I was talking about. Okay, so this corresponds to about 6.78% carbon, and this is weight percent of carbon increases this way. Okay, and yeah, so it's a fairly complex phase diagram consisting of many invariant reactions. So first reaction that comes here is the eutectoid reaction at a temperature of about 727 degrees centigrade. So the scale is in degrees centigrade. Okay, and this is the alpha ferrite phase, right? And we have a eutectic region here. So this will be a straight line throughout, and so here is a peritectic reaction. So there is a small phase field of delta iron lying here. So this is how this looks like. So we see what are the different phase fields that exists here. So we started out with saying that this is an alpha ferrite phase here, and this is the gamma phase of iron. So, and this is, as we say, it is the cementite. So this phase field will be gamma plus Fe3C. This will be alpha plus gamma. This will be between alpha plus Fe3C. This here is liquid, So this is and by the way, this is the delta phase at high temperature phase of carbon, and this here will be delta plus liquid, and here we have delta plus gamma phases, and this phase have gamma plus liquid phase, right? And correspondingly we have Fe3C plus liquid somewhere here. Okay, so we'll just note out the various important reactions, the temperatures that we can see in this diagram. So this is at about 912 degrees centigrade, um, and this set is almost 1400, and this is 1538. So if we take a pure carbon and heat it, so the alpha iron, pure iron and heat it, so alpha iron transfers to gamma iron at about 920 centigrade, corresponding to a change from BCC phase to FCC phase, and that delta iron stays in equilibrium till about 1400 degrees centigrade, where the delta change from gamma to delta change is observed. At higher temperatures, we again come back to the BCC phases. So this is at about 1394, so that's almost 1400. And this peritectic temperature is about 1493. So this here is a peritectic reaction. This here is a eutectic reaction. We have already covered what those terms mean, and since we have a solid phase reaction here, so this phase here is a eutectoid reaction or eutectoid invariant reaction, right? And we'll note on the contents of carbon, which is very important, because as you will see, this help in determining the percentages of phases. So the maximum amount of alpha that can go in iron at 727 degrees centigrade, the eutectoid temperature is about 0.022, and this here, the eutectoid composition is 0.76, and this junction here should have a concentration of about 2% of carbon, and we'll see that for engineering steels we are only bothered with the compositions lying to the left of this 2% boundary. For cast irons, we consider from 2 to 4.58% of carbon. So this eutectic point stays at about 4.3. Okay, and this temperature here is 1147. This is the eutectic temperature, of course, in degrees centigrade. And yeah, I think yeah, that's all the important compositions that we need to keep in mind um, while we are solving problems pertaining to the iron carbide phase diagram. So as I said, like we are only concerned with for steels, we are only concerned with compositions which are less than 2.14. So I'll mark it here, green. Okay, so so all the compositions whose weight percentage is less than 2.14. So this region, you can just write it here somewhere. Yeah. So this are what we call as steel. All form of steel lie in this region, and while this region is called as cast iron. So again we'll see what are the different types of steel. So as I said that within steel also we will be having it can be either hypoeutectoid, or it can be either hypereutectoid, depending what is the composition of the alloy that we are taking with respect to the eutectoid point. So if you just consider this part of the phase diagram, so basically this part of the phase diagram below the 2.14 weight percent. So if our concentrations of carbon lies less than 0.76, we call it as hypoeutectoid, and if our concentrations of carbon is greater than 0.76 within this region, uh, less than 2.14 of course, then we call it as hypo or hypereutectoid steel corresponding. So we'll just go and quickly see what are the different phases that we can get in both the alloys of steel. So if I just magnify the part of the phase diagram towards the steel, or towards the um, steel region, okay. So this is about this, this is about 912, right? And this transformation happens from alpha, and this is gamma phase, if you remember, alpha plus gamma. And this part we are considering that it's a pure cementite phase, and this is the eutectoid point, okay, and this is our alpha, this F3C phase. Okay, so what if for hypoeutectoid, for hypoeutectoid alloys of steel, so we have to lie with below carbon is less than 0.76. So we lie somewhere here. So maybe I'll just draw a vertical line somewhere. Right. So this is our region of existence. Let's say we have a composition of about C naught here. And this is weight percent carbon, this axis, and this is 0.76, and this we have seen is about 0.022, right? And this goes on towards the carbide phase, and then we have well, let's see if what we'll have in different points of the composition C naught here. Let's say this point, this point, this point, and just below the eutectoid temperature, this point. Okay, so let's draw phase fields and see what we get here. So we will be drawing 4 phase fields corresponding to the 4 regions that we have marked in this along this composition. Okay, let's arrange them. Let this be somewhere here. Okay. Okay. Let's see. So for this part, right, we will be having pure delta phase because we are in this delta region. So what we'll be having is pure delta here, right? Grains of pure delta. And just below this, here you will have some precipitation of alpha phase in the gamma phase. Sorry for the mispronunciation. This is gamma phase. So we'll have pure gamma, and then we have the precipitates of alpha or alpha ferrite forming in this gamma phases. Okay, so we'll be having, so this is gamma by the way, and we'll be having small precipitates of alpha ferrite which has just started to form. This will be forming along the green boundaries like this. Okay, and just if we go on cooling it further, so we'll be having certain colonies corresponding to the not colonies, we'll say certain enlarged regions corresponding to both the phases. So the alpha phase, the pro-eutectoid alpha phase, will have grown so much such that we have higher phase fraction of alpha. So this is alpha. Okay, and we have all of it is the alpha phase. Okay, and then if we go on cooling it further, what we will be having is separate laminar colonies of alpha, pro-eutectoid alpha will be separate, and the remaining will be separate out as phase, special phase that we know it as perlite. So this is the pro-eutectoid alpha that we had seen earlier. And we'll have colonies of alpha outside and Fe3C. So these colonies are known by a very special name, perlite. So this laminar structure of the colonies right. So this phase is perlite, which is nothing but alpha plus carbide, that is Fe3C. Alpha is ferrite, Fe3 is carbide. So ferrite and carbide phase is called perlite. And this here, as we said, which was precipitating out early, this is what we call as the pro-eutectoid alpha, right? So this corresponds to, by the way, so this corresponds to this phase region, so microstructure. This is this microstructure. Great. So we have so this pro-eutectoid alpha. This is this region, and we have perlite here, and that perlite consists of eutectoid alpha plus Fe3C, because just previous to the eutectoid alpha formation we had pro-eutectoid alpha, so there is also alpha in this perlite phase. That's we know it as the eutectoid alpha. Okay, and these are the hypo-eutectoid alloys. Similarly, we'll see what are the hyper-eutectoid alloys. Um, Maybe I'll just try to see if we can copy it. Hold on, let's try it again. So we have hyper-eutectoid alloys. So in this case, we are only interested in the compositions which are above 0.76 weight% of carbon. We take a composition here somewhere, and let's say if you mark different points similar to the previous case here. Let's take 3 phase fields for simplicity, and let's say this one, and we'll also draw the regions denoted by the same. Okay, so this is gamma plus Fe3C, by the way. Okay, so here we have this like similar example we have seen for hypo. So this part will be completely gamma phase. This part here we have small precipitates of carbide Fe3C. These are Fe3C precipitates of the at the boundary, and just below this we'll be having this region will be completely the grain boundary will be completely covered with the Fe3C phase. Okay, and we have some colonies like this here. And these colonies are nothing but the perlite. So this is Fe3C, the black part, and perlite will be alpha Fe plus Fe3C. So we have pro-eutectoid carbide in this phase instead of having pro-eutectoid alpha as you have seen earlier. So this here is perlite phase. Okay, and this perlite consists of which consists of eutectoid eutectoid Fe3C plus alpha phase that is present just below the eutectoid point. Alpha will suddenly start to form. Okay, so these are the different phase fields we have for hypoeutectoid and hypereutectoid alloys. So mainly difference lies in the composition, the percentage of the composition, if it is which position relative to this 0.76 eutectoid. Okay, so moving on. So this is how the phase diagram looks like in real in a fair graph. So we can see that not only it's a very small composition, that small amount of carbon that a steel can tolerate, because we are just talking about, the weight percentage is about 2 or 3%, 2% where steel are considered. So it's a very small amount. That too, if you just see the total amount in for alpha, you can see it's like the carbon content is like in very low. It's like 0.022 weight%, which is really low. So it should be appreciated that the amount of carbon that we actually require is very less. It's in like in the single digits of percentages, right? Okay, so this is all the theory that we need to recap, and moving on. So we'll go and solve a few questions based on this concept that we covered. So this question asks, so here is this is a perlite microstructure. You can see colonies of alpha. The red is in alpha, and the Fe3C are these dendrites, right? So this is a perlite structure. So we are being asked for part A. So what are the mass fraction of alpha ferrite and cementite in perlite? So let's say we are here, right? So this is the perlite part. So we have been asked like what are the mass fractions of alpha ferrite? So alpha ferrite and cementite. So Fe3C cementite. So what is the mass percentage? So since we know from this phase diagram that C, so C compositions of Fe3C is 6.7 weight% carbon. You can see it here is 6.7, and C alpha is 0.022 weight%. Okay, so this C alpha is 0.022, which is basically this part. And C naught, let's say we have an arbitrary component C naught, so we need to know what should be the composition or what should be the mass fraction. So for that, like what we need to do is we need to take this portion. We have been asked for exactly perlite without any pro-eutectoid alpha or pro-eutectoid cementite, so we should consider this. We should consider this composition only. Okay, and this is 727 degrees centigrade. This is alpha. Maximum concentration is 0.022. Okay, and this is 0.76, right? And we have been asked for the eutectoid composition. And why we want pure eutectoid composition? Because eutectoid composition has 100% perlite. So eutectoid composition has 100% perlite, right? That's the reason why we should consider only this 0.76, which is my C naught in this case. So C naught is 0.76, and this perlite continues to pure pure Fe3C, which is 6.7 weight% of carbon. Okay, So for finding out, what we need to do is we just need to take a tie line. We need to take a tie line at the eutectoid temperature. So this is gamma. So you take a tie line at the eutectoid temperature, and then just see what are the different what are the different phase frequencies, because at just below the eutectoid temperature we'll be having 100% perlite at this composition. So the mass fractions corresponding to that will be, so since mass fraction of alpha at this eutectoid temperature, just below the eutectoid temperature where 100% perlite is formed, will be this part, divided by this part, right? So this should be 6, that is Fe3C minus C naught divided by the total CFE3C. So this is CFE3C minus C alpha. So plugging in the values, we'll have 6.7 minus 0.76 divided by 6.7 minus 0.022, which gives me about 89 fraction, that is about 89%. So this is the weight fraction or the mass fraction of alpha in 100% perlite. Similarly, we'll be having what is the mass fraction. The other phase is cementite, of course. So not mass of fraction, rather mass fraction. Mass fraction of Fe3C in 100% perlite. Okay, so this will be given by, this tie line can be given by, so this composition can be given by Fe3C will be this part, right, which is C naught minus C alpha. By the total thing is CFE3C minus C alpha, which gives me 0.76 minus 0.022 divided by 6.7 minus 0.022. That gives me 0.11, which is complement of this, right? So these are the mass fractions of alpha and alpha ferrite and cementite. So we have 89% of alpha and 11% of cementite, right? So if you have a colony like this, you can see, so the alpha will be covered by about 89%, this will be 89%, and this will be about 11%, which is also very apparent in this case, because you see these are like very thin, so the mass fraction will be expected to be lower, right? Okay, great. So coming to the second part of this question, what is the carbon concentration of an iron carbon alloy for which the fraction of total ferrite is 0.94? Okay, so we have been told that what is the fraction of total ferrite. So weight fraction of total ferrite is 0.94, and just applying the same formula that we have applied in the previous part. So weight fraction of alpha can be given by CFE3C minus C naught, let's say CX. It's a known composition that we need, divided by CFE3C minus C alpha, that is 6.70 minus Cx divided by 6.70 minus 0.022. Okay, so if we just solve this equation, we just write the values. 6.70 minus 0.022 is about 6.678. 6.678 multiplied with 0.94 is about, so Cx is 6.678 70 minus 6.277. That gives me about 0.423% carbon. So see, 0.423 weight% carbon is less than 0.76, by the way. So it was most probably it was a hypoelectroid alloy, right? But we have not been asked. So if it has been asked, you just know that what is the concentration relative to the electroid composition. So what is the total carbon concentration? This is the answer. Okay. So moving on to the next question. So it asks, like, what is the proelectroid phase of an iron carbon alloy? So proelectroid, we don't know if it is proelectroid. Is it alpha or is it Fe3C? We don't know. Okay. For an iron carbon alloy in which the mass fractions of total ferrite and cementite, so mass fraction of total ferrite is given by 0.92. Okay, and the mass fraction of total cementite is given by 0.08. So this is just an extension of the previous question. So we just know that what is the mass fraction of alpha, right? So what is the mass fraction of alpha? As per our previous equation, we have seen it is Fe3C minus C naught divided by CFE3C minus C alpha, which gives me 0.92. So this is 0.92. And upon solving, I can just plug in the values. So this is 6.70 minus C naught, which is unknown, divided by 6.70 minus C alpha, which is 0.022. That is 0.92. And upon solving, this gives me 6.70 minus 0.022. And subtracting from 6.7, it gives me about 0.556 weight% carbon. Okay, so this is the original concentration that we had taken. So now we must know the original concentration, so we can find out what is the proelectroid phase. Now you can see that 0.556 is greater than our it's lower than our 0.76, right? So 0.76 weight%. So that tells us that this lies in the hypoelectroid region. So it's a hypoelectroid alloy. So my proelectroid phase is nothing but alpha, right? So so what is the proelectroid phase composed percentage? So for that we just need to imagine, like, if you are in this phase diagram, so this is 0.76. So we are somewhere here with 0.55 weight%. So naturally, what proelectroid phase we will be having? So the question says what proelectroid phase. So the answer is basically we have pro-eutectoid phase is nothing but alpha. Okay, so I hope this is clear. This is a hypoeutectoid alloy. All right. So moving on to the next question. So we have been asked, like, we have 1 kilogram of austenite. So austenite is basically the gamma phase containing 1.15 weight% carbon, cooled to 727 degrees centigrade, and we know 727 degrees centigrade is the eutectoid temperature. Okay. So so we have been directly given the concentration of original concentration is 1.15 weight% carbon. So 1.15 weight% carbon corresponds to, since it's greater than 0.76, so this is a hypereutectoid. This is a hypereutectoid alloy. So what is the pro-eutectoid phase? Naturally, if it is a hypereutectoid alloy, so my pro-eutectoid phase should be Fe3C, right? So this is the answer for this part. So second part asks how many kilograms each of total ferrite and cementite form. So total ferrite and cementite. So we just know that what is the weight% of alpha for hypereutectoid. So weight% of alpha can be given by C0 minus, so CFE3 minus C0 divided by CFE3C minus C alpha, and this is because we are somewhere here, and this is 0.76, this is 0.022, and it goes on till 6.7 weight% is carbide. Okay, so what is the percentage of alpha then in this total? So what is each total ferrite? So total ferrite can be given by C0. Let's say this is C0. So this portion, right? So this is alpha phase. So correspondingly, lever rule tells us that the percentage will be calculated by the arm that is opposite to it. So arm that is opposite to it is this one, divided by the total arm, right? This is the total arm. So that is Fe3C is 6.7 minus C0 is it's given already is 1.15 divided by 6.7 minus 0.022, and this gives me about 83% of ferrite. Okay, so since this is the mass fraction, so the total amount in mass is 0.83 times 1 kg, which gives me 0.83 kilograms of alpha ferrite. So this is the correct answer. Remaining part, so it's, you can also apply lever rule to get the weight of the the remaining Fe3C phase. So total cementite can be also, because it's just a complement, so WFE3C plus W alpha is equal to 1. Therefore WFE3C is equal to 1 minus W alpha, which is 1 minus 0.83, that is 0.17. Therefore mass of cementite in alloy is 0.17 fraction of 1 kg, that is 0.17 kilograms. So this is the answer for number B. Okay, now coming on to the part C, we have been asked like how many kilograms each of perlite and proetectoid phase form. So how many kilograms each of perlite and proetectoid phase are forming here. So in that case, for calculating the percentage of perlite, what you have to do is we have to take ratios corresponding to the this region, ratios corresponding to the eutectoid composition, right? So now this will tell us that what is the perlite composition. So my perlite composition should be this region, perlite amount rather, sorry, the perlite composition is 0.76. This region divided by this part. Okay, so because for perlite this is the phase boundary, rather the phase composition here. So opposite arm of that is this one, which is 6.7 minus C naught. So W let's say perlite is P is C Fe3C minus C naught divided by CFE3C minus CE or CP. It's perlite composition. CFE3C is 6.78%. C naught has been given to us as 1.15 divided by CP. You all know from phase diagram is 0.76. That gives me about 93% of perlite. So corresponding to, and this corresponds to a mass of 0.93 kilogram because the total alloy is 1 kg. Okay, so correspondingly weight fraction of the proetectoid phase can be given by, so the proetectoid phase here is Fe3C, and Fe3C is given by this region, right? Because Fe3C is this, so opposite arm to this is this. So C naught minus 0.76. So C naught minus 0.76 divided by CFE3C minus 0.76. That gives me 1.15 minus 0.76 divided by, so I could have written this as CE. Uh, 6.70 minus 0.76. Let me check if I'm right. Yes, I'm right. This should give me about 0.07 mass fraction of proetectoid ferrite. That corresponds to 0.07 kilograms of proetectoid ferrite. Okay, so this is the Cth part of this question. So last part asks us to schematically sketch the microstructure. So let's see. So how will the microstructure look like? So we already know that we are in the hyper-detectoid alloy regime. So here there's no doubt that we will be having proetectoid Fe3C in the microstructure alongside perlite, coexisting alongside perlite, right? So here we should pay attention to the geometry of the different phases that we are drawing. So we know that we should have a proetectoid phase first. I should rather draw consistent color. So we had drawn cementite with black, so we'll keep that same scheme. Okay, so this here protectoid. Ferrite. So and correspondingly we'll have colonies of ferrite and sorry, this is cementite, protected cementite, and we have colonies of ferrite and cementite, which is known as perlite. So here this is alpha ferrite, and the colonies in between alpha ferrite is our detectoid ferrite, cementite, sorry, so detectoid cementite. Okay, so this entire thing will give us this microstructure, which is the upper case. Okay, and this together, so alpha ferrite and eutectoid, so this and this will give us this entire thing is what we call as the perlite phase, right? So the colonies are laminar colonies. We call it perlite. Okay, great. So moving on to the next question. So we have been asked, like, compute the mass fractions of pro-eutectoid ferrite. So pro-eutectoid ferrite, so it is a hypo-eutectoid, and perlite. So pro-eutectoid ferrite and perlite that form in iron carbon consuming 0.58%, which is naturally less than 0.76. That's its reason it is hypo-eutectoid. Right. Okay. So we have already seen in the previous question. So in case of hypo-eutectoid, let's quickly draw it so that it's not confusing. So we are somewhere here. With 0.25% of carbon, this is 0.76, this is 0.022, so alpha gamma alpha plus gamma alpha plus F3C gamma plus F3C. This is our perlite. Okay, this is our perlite. So we have been asked what is the mass fraction of pro-electrolyte ferrite. So pro-electrolyte ferrite will be, so this is by the way 0.25, right? Yeah. So if we just take this part, we take this part, which is Cp minus C naught divided by Cp minus C alpha. It should be Cp 0.76, C naught is 0.25 by 0.76 minus 0.022. This should give me about 0.69% or 0.69 mass fraction or 69%. 69% is my pro-electrolyte, so this is mass fraction of pro-electrolyte ferrite. Okay, and that's the reason why we are mentioning it with the prime. It's a pro-electrolyte ferrite. Similarly, so the mass fraction of perlite can be given. So perlite is this boundary, so opposite arm is this one. So this divided by the total arm. The total arm is this. So Wp can be given by C naught minus C alpha. So this is C alpha here. This is Cp C naught minus C alpha divided by Cp minus C alpha, which is 0.25 minus 0.022 divided by 0.76 minus 0.022, which gives me about 0.31. So 31% of perlite. So this is the mass fraction of perlite, which also contains ferrite and cementite. So this is the ferrite that is inside the perlite, and it amounts to a total of 31%, and while the ferrite which is outside perlite is about 69%. Okay. Great. So moving on to the next question. Right, so we have been asked like what is the mass fraction of total ferrite and total cementite in an iron carbon alloy. So these are the mass fractions are given. So we have been asked, is it a hypo-electrode or hyper-electrode alloy? So to know that, we have to know the actual composition of the or the original composition of the alloy that we're considering. So, and if it lies below 7.76, we can tell it hypo, or if it is more than 7.76, it has to be hyper, right? Okay. So let's see what we have been given with. So we have been given the mass fraction of total ferrite. So this is total ferrite, by the way, is 0.88. Okay, and if I draw a phase diagram, so total ferrite should be given by so we don't know where the composition lies right now, but the total ferrite should be given by the arm which is away from it, right? So it should be 6.7 minus C naught, which might be here or here, divided by 6.7 minus 0.022, right? So this should be given by arm which is away from the alpha phase. So this is the alpha phase. arm that is away from alpha phase is 6.7, or if you write it in terms of concentrations, Fe3C minus C naught, and the total arm is 6.7 by C alpha, which gives me 6.70 minus C naught, which is unknown here, divided by 6.70 minus 0.022. And upon solving this should give me C naught should be about 0.828% carbon. Okay, so 0.828% carbon, and since our C composition of pearlite, or the tetroid composition is composition at 100% pearlite is 76%, which is lower than C naught. Therefore, the alloy is hyperetectoid. Okay, so this is what the question was asking. So this is the answer. Okay, now let's see if we can draw it for proper representation. This is equal to 0.82. So alpha fraction can be given by this divided by this. Okay, so this is what we employed. We can also employ this for the cementite. So cementite will be nothing but the complement of it. So cementite also, if you want, let's say if you want to write the equation for cementite, it's pretty easy. So cementite is here. So since cementite is here, the opposite arm should be towards ferrite. Oops. So the opposite arm opposite to cementite is here, right? So this part. So if you have to write equation after all for the total cementite, you can write it as C sound should be from here. So the equation for total cementite should be C naught minus C alpha divided by Fe3C minus C alpha. If we equate it to 0.12, you can calculate C naught. That should give me this answer also. Okay, so we can solve it either ways because they are complementary each other. Moving on, so in the next question we have been asked, the microstructure of an iron carbon alloy consists of a pro-eutectoid ferrite and pearlite. Okay, so similarly, so pro-eutectoid ferrite tells me this is a hypoeutectoid alloy, and of course pro-eutectoid alpha should exist with a pearlite phase. Okay, so the mass fractions of these constituents are so this alpha, W alpha prime, which is pro-eutectoid, is 0.20, and W pearlite is 0.80. Determine the percentage of carbon. So similarly, what we have seen in this case, in the previous case. So in this question, yeah. So if you want to find out the weight fraction of pro-eutectoid alpha, you can get it by taking a tie line here and then drawing So since we are in hypo region, so we can take some composition in this part, which is C naught, and this is our perlite. This is perlite Cp, and this is C alpha here. This here is C alpha. So we have been given a concentration of weight fraction of the proetector alpha. Proetector alpha is nothing but, if you consider this as the phase field of alpha, so the opposite arm is this one. So W alpha prime is given by Cp minus C naught divided by Cp minus C alpha, which is Cp is 0.76 minus C naught divided by 0.76 minus 0.022, and upon solving, and this is given as so this has already been given in this question as 0.20, right? So upon solving, so 0.76 minus 0 C naught divided by 0.74 is equal to 0.20. Upon solving, we get C naught as 0.61 with carbon, which makes sense also because this is less than, should be less than, because if it is precipitating out proetectoid alpha, it should lie less than 0.76, which is what our answer also says. So it's the concentration of carbon that we were asked. So moving on to the next question, number 7. So we have been given 2 kilograms of 99.6 weight percent iron and 0.4 weight percent carbon, and this is what we need for calculation. That is cooled to a temperature just below the eutectoid. So eutectoid temperature is 727 degrees centigrade. So how many kilograms of the proetectoid ferrite form? So pretty simple, like proetectoid ferrite can be given by the equation that we derived in this previous slide here. So which is Cp minus C naught divided by Cp minus C alpha. Cp is 0.76 minus C naught have been given as 0.4 divided by 0.76 minus 0.022. Upon solving, this should give me about 49% or 0.49 mass fraction of proetectoid ferrite, and since my total mass of the alloy has been given as 2 kilograms, so the mass of, so absolute mass of the proetectoid alpha is 0.49 times 2 kilograms. That should be 0.98 kilograms of proetectoid alpha. So how many grams of eutectoid ferrite? How many grams of eutectoid ferrite? So we all know that eutectoid phase is perlite, which consists of eutectoid ferrite plus cementite, right? So to calculate that, we need to know the total amount of ferrite, the total alpha, right? And total alpha can be given, we have seen in the previous example, the total alpha can be given by the total arm between away from the ferrite phase field, between the composition and the carbide phase, divided by the total arm between CFE3C and C alpha. Okay, and that should give me 6.70 minus, we have been given 0.4 divided by 0.022. That should give me 0.94 or 94% total. I have ferrite in that, right? So if I just take the weight of that, so mass of total ferrite is 0.94 times 2 kilograms should give me 1.88 kilograms. Therefore, we can tell that mass of the eutectoid ferrite, since total ferrite consists of eutectoid ferrite, which is formed in perlite, by the way, and we have the pro-eutectoid, which is already formed before the eutectoid point. Therefore, eutectoid ferrite W alpha is given by total alpha minus W alpha prime. Right? Total alpha we have been given as 1.88 kilograms, alpha prime we have calculated as 0.98 kilograms. That should be 0.9 kilograms or 900 grams of eutectoid alpha in the alloy. Okay, so this is what the question asked. Number B. Number C asks, how many kilograms of cementite form? So cementite is also pretty complement of what is alpha. So total alpha is we have calculated total alpha to be 0.94. Yeah. So total amount of cementite that forms. So the total amount of cementite forming will be inside the inside the perlite phase, because perlite phase consists of eutectoid alpha, which we have calculated, and ferrite and the cementite phase. So we need to apply the lever rule. So C naught minus C alpha divided by Fe3C minus C alpha. So this is pretty easy to see again, because let's say if you have phase here, right, and we are somewhere here, right, because it's a hypoeutectoid alloy, and this is 0.76, this is 0.022, and this is alpha, and ferrite is towards the right. So if I want to calculate the fraction of ferrite, calculation of the fraction of cementite, sorry, so we need to take the arm that is away from the cementite phase. So this is the arm that is away from the cementite phase, divided by the total arm, right? So the arm that is the arm of the lever that is away from the cementite phase is C naught minus C alpha, divided by the total arm is CFE3C minus C alpha. Okay, so if you just plug in the values, what is the C naught we have been given? 0.4 minus 0.022 divided by Fe3C is 6.7 minus C alpha is 0.022. That gives me 0.057 weight fraction, or the total mass given by multiplying this phase fraction times 2 kilograms. That should be about 2 kilograms. That should be 0.114 kilograms or 114 grams of cementite we have in the alloy. So the next question, number 8. So we have been asked, like, what is the maximum mass fraction of pro-eutectoid cementite possible for a hyper-eutectoid iron carbon alloy? So for this, we have to visualize something. Okay, so hyper-eutectoid lies above the eutectoid concentration here somewhere. So let's say we have a hyper-eutectoid composition of C0, and this is Cp corresponding to the perlite composition, and this is C alpha, and of course the right side is Fe3C. Okay, so yeah, so the cementite that is possible. So we have been asked the mass fraction of pro-eutectoid cementite. Of course, if we are in this region, so we'll be precipitating out Fe3C and not alpha, right? And this is the perlite phase, 100% perlite phase here. So what is the maximum amount of it? So maximum amount of cementite can be given by this here, right? And since this here is now 4.76, 2.022. So this is about 6.78%. So if you see what is the cementite weight here, the cementite weight can be given by this divided by the total. Right, and there's a limit, by the way. So if you see the phase diagram of iron carbon, so yeah, so you see that this region, right, there's a limit to which you can go up to which the eutectoid or hyper-eutectoid point lasts. So hyper-eutectoid region lasts from 0.76 to 2.14, right? So and if you want to know the constant, if you want to know what is the maximum amount of cementite that is possible, so cementite is given by this arm, right? As I said, cementite is given by this arm divided by the total arm, right? And if the cementite, what is the maximum we can go? Maximum we can go up to this only. We can't cross this part because then it will not be a steel. It will go into the cast iron region. So the maximum arm it can go is this 2.14. So this arm can go to 2.14. Now we just need to plug in there to calculate the total fraction. So this can go maximum up to 2.14. So C0 we can go up to 2.14%. So therefore maximum percentage of cementite can be given by the C0 minus Cp divided by Cfe3C minus Cp, which is C0 is 2.14 minus 0.76 divided by 6.7 minus 0.76, and that should give me about 0.232 or 23.28%, right? This is the answer. So what is the maximum mass fraction? The maximum mass fraction is about 23 percentage in percentage and 0.23 in mass fraction that is possible for pro-eutectoid cementite to be present in a hyper-eutectoid iron carbon system, because after that basically we'll be going in this region of cast irons, right? So after that we'll be having whatever we'll be having is cast iron, not steel. Okay, so this is the maximum amount of cementite. Okay. So moving on to the next question, we have been asked, is it possible to have an iron carbon alloy for which the mass fraction of total ferrite, so mass fraction of total ferrite is 0.846 and mass fraction of pro-cementite is 0.049. Okay, so mass fraction of total alpha is given here, so we'll just plug in the equation. We know if we have been given its pro-ectectoid cementite, so for sure we are lying in the hyper-ectectoid regime. So we are somewhere here. Okay, this is 0.76, 0.022, this is 6.7. 727. So is it possible to have an iron carbon alloy? Is the mass fraction of total ferrite? So total ferrite is given by the arm which is away from the ferrite phase field. So this is our ferrite phase field. The arm that is away from this is this arm, and if we divide by the total arm length, we should get the mass fraction of total ferrite. So 0.846, which is given to us, is CFE3C minus C0 divided by CFE3C minus C alpha, which is 6.70 minus 0.022 divided by 6. Oops, this should be this is what we don't know. Sorry, C alpha is 0.022. So if we just plug in the values, we should get C0 is 0.846. Now yeah, so sorry, so 0.846 was the RHS. Sorry, so this should give me C0 should be 1.05. 1.05 weight percent of carbon, that is here. So of course it is greater than 0.76. That's the reason why we call it as a hyper-ectectoid steel, right? So now we write the same equation for pro-cementite. So for pro-cementite, we should take this part divided by the total this part, right? So maybe if I just write it, okay, so pro-ectectoid cementite, this is cementite phase. So the arm that is away from cementite phase is this, and if we divide it by the total arm length from perlite phase from here, that should give me the mass fraction of the pro-ectectoid cementite. So pro-ectectoid cementite will be therefore C0, this is C0 minus Cp divided by the total here is CFE3C minus Cp, which is C0 is we don't know C0. Cp is given by 0.76 divided by Fe3C, we know it is 6.70, Cp is 0.76. On solving this, we should get C0 to be 1.05 weight percent, which matches, right? Even if we approach it in this way or if we approach it this way, we have same answers for the both cases. So hence this hyperutectoid alloy is possible. There's no doubt it's not possible. Okay. Great. So moving on to the next question. Is it possible to have an iron carbon alloy for which the mass fraction of total cementite and pearlite? So mass fraction of total cementite and pearlite is given. So we can write it. Cementite, weight fraction is 0.039, and pearlite 0.417. So for solving this, we have to set up a lever rule expression for both of this mass, and then you have to just solve it. If you see C0 values are coming same for both, then this alloy is possible. So the mass fraction of total cementite mass fraction of cementite should be given by the arm that is away from the cementite phase, that is C0 minus C alpha. Divided by the total CFE3C minus C alpha, which is C0 minus 0.022 divided by 6.7 minus 0.022. Solving this, we get C0 value as 0.28 weight% carbon. Okay, so this is what we get by solving this from first mass fraction of cementite. Now mass fraction of pearlite, right? So mass fraction of pearlite can be given by the arm that is away from the pearlite region. So that should be given by C0 minus C alpha divided by. So it's easy to imagine also. So if let's say if our composition is less than 0.76, so if it is lying here somewhere in this region, let's say if lying here somewhere, then the arm that is away from the pearlite phase, this is pure pearlite phase, is this arm, which is basically the arbitrary composition C0 minus 0.022, that is C alpha. So C0 minus C alpha divided by Cp minus C alpha. Which is C0 minus 0.022 divided by Cp is 0.74 minus 0.022, and that is given to us as 0.417. Now solving this, we should get C0 value as 0.33 weight% carbon. And as you can see that the answer in both cases, are not matching. That tells us that such an alloy is not possible that can simultaneously satisfy the total mass fractions of cementite and pearlite as given here. So such alloy is not possible. So coming over to the next question. So compute the mass of eutectoid ferrite. So we have eutectoid ferrite in iron carbon alloy containing 0.43 weight% carbon. So 0.43 is less than 0.76, so it is a hypoeutectoid alloy. So we should be somewhere here. Right, this is about 0.022 C alpha, this is C naught, this is Cp, and CFE3C is at the rightmost. Okay. So you can see that first of all we need to find the total ferrite, and then if we subtract because total ferrite is basically distributed in pro-eutectoid ferrite, and we have eutectoid ferrite, right? So we just need to deduct pro-eutectoid ferrite from total ferrite to get the eutectoid ferrite. So how will you do that? So pro-eutectoid ferrite can be given by this part, this arm divided by this arm. Okay, so pro-ferrite basically W alpha prime can be given as so it can be given as Cp minus C naught divided by Cp minus C alpha. This is the pro-eutectoid ferrite composition, and upon evaluating the value 0.76 minus C naught value is given to us as 0.43 divided by 0.76 minus 0.022. That gives me weight plus the mass fraction of the pro-eutectoid ferrite as 0.446. Okay. So similarly, the total alpha is again easy to see. In that case, you have to see the range. This one, the total. So alpha is this field, by the way. So you have to consider the range opposite to this phase field. So this range divided by the total range here should give me the weight fraction of total alpha. Weight fraction of total alpha is therefore CFE3C minus C naught divided by CFE3C minus C alpha. That is 6.7 minus 0.43 divided by 6.7 minus 0.022. That should give me about 93% or 94% of total alpha. So therefore W eutectoid alpha can be given as the difference between the total alpha, this is total, and we had about 0.446 existing as alpha prime, right? So this should give me 0.493 or 49.3 weight percent of eutectoid ferrite. Therefore mass fraction of eutectoid alpha is 0.493, and this is present in the perlite, and the alpha that is outside of perlite is the eutectoid alpha. Okay. Great. So next question, number 12. We have been asked the mass fraction of eutectoid cementite in iron carbon alloy is 0.104. So W eutectoid cementite. So Fe3C is given as 0.104. On the basis of this information, is it possible to determine the composition of this alloy? If so, what is the composition? Yes, it is possible. Let's see how. Okay, there are two possible answers. For first case, the tetroid cementite exists. Let's see the case 1. The tetroid cementite exists. In addition, pro-tetroid cementite. Means assuming if there is a pro-tetroid cementite, we assume it's a hyper-tetroid alloy case. Okay. For this, the mass fraction of the tetroid cementite is difference between the total mass fraction of total cementite minus mass fraction of cementite existing as pro-tetroid cementite, right? So we have seen in the previous equations, the total cementite equation can be given by C naught minus C alpha divided by CFE3C minus C alpha, and the tetroid cementite will be given by C naught minus C naught minus Cp basically divided by Cp minus C alpha. So just plug in the values and we should get C naught, we don't know, so we need to find out C naught. So C naught minus 0.022 divided by 6.7 minus C alpha. C naught minus 0.76 divided by I think there's a mistake somewhere, so it should be so pro-tetroid cementite. So pro-tetroid cementite should be C naught minus Cp divided by CFE3C minus Cp. Okay, got it. So it should be CFE3C minus Cp. Right. So C naught minus Cp is 0.76 divided by 6.70 minus 0.76, and this has been given to us as 0.104. So solving this, we should get C naught value should be 1.118% carbon. Okay. So this was case 1, assuming that this was a hyper-tetroid alloy. So assuming, let's say we have a hypo-tetroid alloy. Assuming we have a hyporeductoid alloy. So in this case, all cementite is present in the perlite, right? Because here there is no protectoid cementite. The eutectoid cementite in the perlite phase as eutectoid cementite. Therefore, in this case, we have to write Fe3C equation as C naught minus C alpha divided by Cp, Fe3C minus C alpha. Okay, so that is C naught is given by C naught, C alpha is 0.022 divided by Fe3C 6.78% and 0.022, and this should give me 0.1. So upon solving this, we have C naught as 0.72 weight% carbon, which is like very close to 0.76 weight% carbon with electrode composition. So we have two answers for this question. So it is possible for this composition having the total mass fraction of eutectoid cementite of 10.4% is possible for both hypereductoid case and hyporeductoid case also, but of course with different concentrations of total carbon content in the alloy, right? Great. So we have next question for an iron carbon alloy of composition 5 weight% iron, 5 weight% carbon, 95 weight% iron. Make schematic sketches of microstructure that would be observed for the following conditions. Okay. For this case, we need to borrow this iron carbon phase diagram. This one. So we just borrow it here. Okay, now let's just solve the question. Okay, so we have been given different so we should draw three-phase field, phase microstructure fields. So here, and here. Okay. So we have been asked to draw the schematic structure of the microstructure that would be observed in the condition of very slow cooling. And when you say very slow cooling, this is equilibrium, and that is how our iron carbon or any phase diagram that we study, these are all equilibrium phase diagrams. This is what you have to remember. So you can apply this phase diagram. Otherwise, if it was non-equilibrium cooling, this phase diagram would not have been valid. At 1175 centigrade. So 1175, 5 weight%. So 5 weight% is here. So we are at this region, right? Maybe I can just draw a line instead. So we are at 5 weight% of carbon and at different temperatures. So starting out with 1175. 1175 is here. 1175. So this is about 1147 by the way. Okay, so eutectic temperature in this phase diagram is 1147. So 1175 should be here. Okay. So for, let's say this is 1. Let's say 1. Let's say, so at 1175 degree centigrade. So what we have is Fe3C plus liquid, right? So we'll be having Fe3C phases Fe3 phases, and remaining part is all liquid. Of course, the concentration can be given by the diagram, which I'm not mentioning in this case. Great. So at 1145 is just below the eutectic temperature here. So let's see 1145 here, just below the eutectic temperature. So we should have the condensed phases of the gamma, not liquid, right? So we should be having, so the all cementite, the proeutectic cementite should be there, where it was, albeit a bit bigger because they might have grown a bit. Right, and again we should have a colony of other features also. We should also have a colony like this. So this was my proeutectic cementite, and these are my gamma phases that we have. The white one is, let's say, gamma, and Fe3C, these are all my eutectic cementite. Black one inside the colonies. Great. So in third composition is 700. So turns 700 temperature. Sorry, 700 degrees. This here. This point. 700 degrees centigrade. So we should be having alpha plus Fe3C. So we'll be having the same morphology, but the gamma will have converted to alpha. It's important to distinguish the two phases whenever we are drawing. So in this entire slide I have kept cementite phases to be black and ferritic phases to be red and gamma as white, so that there's no confusion between schematically, what are the different types of phases I'm representing by different stroke of colors. So this is Fe3C, which is pro-eutectic Fe3C, and this is my eutectic Fe3C in coordinates. And the remaining part I should be having is alpha, which is what I show in the red color. So it's very interesting to see that whatever phase was delta, it has just converted to alpha. So very similar to how a pure iron should behave. If we cool down iron from high temperatures, we see this. You see, we have the delta. It's not delta, sorry, gamma to alpha conversion at 912 degrees centigrade. But in this eutectic cases, we see the transformation happening at much down below 727 degrees centigrades. So yeah, so all of these are the eutectic alpha ferrite basically. Okay, so these are the microstructures that we were asked to draw or sketch. So coming on to the next question. So it has a we have been asked that what is the volume fraction of the no rather the what is the composition, I guess, that we need to make a alloy of this composite hardness. Okay, so for this is the rule of mixture, by the way, for composites, wherein the properties are related or weighed as per their volumes or the amounts, mass or volume maybe. So in this case we are taking the specific property, let's say elastic modulus and hardness or anything. And the alpha and beta are the different phases of microconstituents. Employ the relationship above to determine the approximate brittle hardness of so weight percentage or C naught has been given to us as 0.20 weight% carbon, assuming the brittle hardness are given, right? Brittle hardness of 80 and 280 for ferrite and pearlite. So simply, if we know the hardness, so basically the hardness of the alloy as per the rule of mixture should be hardness of ferrite, that is alpha, to the volume of alpha, plus the hardness of pearlite into volume of pearlite. So what we need is the volume fractions of alpha and the pearlite, right? So we don't have enough sufficient information because volume fraction conversion also require the density. So we don't know the density. So we assume that this should be a mass fraction correlation, because otherwise conversion of mass to density, mass to volume should require the density, which we have not been provided in this case. So we'll assume the mass fraction of alpha and pearlite. Mass fraction of alpha is given by C naught minus C alpha divided by Cp minus C alpha, that is C naught is 0.20 minus C alpha is 0.022 divided by 0.76 minus 0.022. Check. So this should be about 0.24. Similarly, the mass fraction of pearlite can be given by C P minus C naught divided by C P minus C. That should be Cp is 0.76 minus 0.2 divided by 0.76 minus 0.022. That should be 0.76, which is a complement of this. So you can just subtract it from 1 and you can get 0.76 anyways. Therefore, original hardness of the alloy can be given as H alloy is equal to hardness of 80 for ferrite, so 80 times 0.76 is 280 times, so sorry, I think I mismatched it. 0.24 is alpha. Oops, I think I have mismatched it. Yes. So this was the weight percentage of perlite, by the way. This should be perlite and this should be alpha. Sorry for the confusion. This is alpha and this is perlite, right? So this is 280 times 0.24. Yeah, alpha is 0.24 and we have correct, this is correct. So this should give me a hardness of 128 Bell hardness of the alloy. So it's pretty easy to see that we have 76% of perlite which has a high hardness of 280, right? That's the reason why we see net high hardness of the alloy itself. So next question. We have a steel alloy containing 97.5 weight% iron and 2 weight% molybdenum and 0.5 weight% carbon. What is the electrode temperature of this alloy? So electrode temperature, you can just get it if we have a plot like this. So electrode temperature, what you have to do is you have to just take the concentrations. Let's say here we have been given 2 weight% of molybdenum. So 2 weight% molybdenum is this, and then we have 0.5 weight% carbon. So no carbon is not been given, and yeah, so it's about here 2 weight% molybdenum, and we'll just take an intercept. So this is the electrode temperature of this. It can be given by the intersection of this point with the y-axis, which is about 850 degrees centigrade. What is the electrode composition? So 850 degrees centigrade, you just have to take, similarly you have to take the molybdenum 2 weight%. So molybdenum, this is molybdenum 2 weight%. So here, right here, so this comes out to be electrode composition of 0.22 weight% carbon. So this one, this is this. What is the pro-electrode phase? Now if it is a composition of alloy, since the composition of alloy is composition of molybdenum that we have been given is 0.5 weight%, which itself is greater than my electrode composition. See, let's say electrode molybdenum. Therefore, it is a hyper-electrode case. So in this case, cementite should be the electrode phase. Okay. Assume there are no change in positions. Okay. So these are the assumptions that we have been provided with. So this is the answer. Okay. So I guess we'll have time for one more question. A steel alloy is known to contain 93.8 weight% of 93.8% of carbon. Nickel is 6 weight% and 0.2 weight% carbon. What is the approximate electrode temperature? So in this case, again, we have to employ the same graphs. So we'll just copy the graphs over there. Great. So we have been given, we have a 6 to 8% nickel in the alloy. So nickel is this and 6 to 8% is this, right? So if we take an intercept, it should come out between about 650 degrees centigrade. So the tectoid temperature, this alloy from this diagram, it can be approximated at 650 degrees centigrade. Great. Um, then what is the prototype phase? So for prototype phase nature, we have to know what is the composition, electrode composition. So electrode composition you can get by this part. So 6 to 8% nickel. So nickel 6 to 8% is here, right? If we take an intercept, it should be just above 0.6. So electrode composition is 0.628% carbon. This is carbon, not molybdenum. This is nickel, right? Yeah. So electrode composition is 0.628% carbon, and since carbon we have is 0.28%, so we lie in the regime of hypoeutectoid. I should have a hypoeutectoid alloy. Therefore, the proeutectoid phase is expected to be ferrite. Right? Great. So compute the relative amounts of the proeutectoid phase and perlite. Great. So the relative amounts, assume that the alpha and alpha plus Fe3C phase boundary is at a negligible carbon concentration. So we should have 8% or weight fraction of the proeutectoid ferrite should be 0.62 minus C naught divided by 0.62 minus 0. So negligible carbon concentration, that's the reason why you have C, this is 0, and it should give me 0.62 minus 0.20 divided by 0.62, that is 0.68. Similarly, if we just take the perlite phase should be a complement of that, so that should be C naught minus 0 divided by 0.62 minus 0, that is 0.20 divided by 0.62, which is 0.32. So these are the relative amount of proeutectoid. So this is proeutectoid ferrite, this is a hypoeutectoid alloy, and this is perlite present in this alloy. Okay, so this was the question that we were asked. Great, so that should be the last question. I guess we have crossed the time. Great, so this week we had solved questions mostly on the iron carbon phase diagrams. Specifically, we have seen how different concentrations in the hypoeutectoid and hypereutectoid regime leads to different phase formations at different temperatures, and also what are the relative amounts of the proeutectoid ferrite or proeutectoid cementite phases in hypo or hypereutectoid regimes respectively. So this is an important part for engineering alloys, because steels are mostly widely used, and then for calculating the mechanical properties you should know what phases are present in the steel, and the amount of phases are necessarily important, that determines the strength, and that can be determined with this phase calculations. So that should be all for this week. So hopefully we'll see come back next week and we'll solve more questions based on the contents covered then. So thank you so much for attending. Hope to see you soon next week. Thank you.